I think Imre, you can start.
Thank you so much. I accepted the recording. Then start. Good morning, good afternoon, good evening to each of you, depending on from where you follow this presentation. Actually, it is a very sad day today. This is what we just discussed with the kind professor colleagues, because this is the last day of the course, which will conclude with a end examination in the afternoon. So we came to the end of the designing of cyber-physical systems for general social and personal utilization core. Nevertheless, I prepared interesting topics for you, and the first presentation, the 19th one, will be about designing for adaptation and evolution. The first block will be concentrating on the issues of adaptation, and the second block goes into the system evolution issue. So let's start with a discussion on the forms and methods of system adaptation. In order to position you in my mental model, we have to revisit the well-discussed computational smartness cycle. So on the smartness spiral, we have discussed already sensing issues. We discussed building awareness and context management. We discussed different approaches to reasoning and also extensively the aspect of system level learning, strategic learning. What remains is actually the operation planning, which includes topics like changing reference workflows, applying reactive planning, applying runtime planning, and forecasting simulation. And the last is the runtime adaptation of the system, which obviously includes aspects like changing analog devices, changing software components, changing cyber contents, actuating effector networks, and resetting control instruments. So as a kind of setting of the stage, let me tell you following things. Although the phenomenon of system adaptation is currently a hot issue, it is known only partially in the case of complex engineered systems. In biology, however, the adaptation is defined as the process of subsequent changes by which a living organism or a community of organisms becomes better suited to its environment and increases its chances of survival. Initially proposed for natural systems, this interpretation implies four assumptions. First of all, adaptation is towards a goal, purpose, or situation. Second, adaptation is not a one-time action, but a purposeful sequence of changes. Third one, adaptation is performed by the subject of the changes themselves. The fourth one, adaptation is to be put into the context of interaction with the environment or a community of organisms. The same principles have been applied to engineering systems, but still there is no general system adaptation mechanism available for the developers and practical use. However, we are moving towards this goal, and there are some milestone achievements in this role. First of all, the theoretical understanding of the sense of adaptation is better now. And we know that adaptation naturally happens and safeguards survival of independent individuals, no matter if they are natural or artificial. Adaptation is necessitated when a system is not doing what it is intended to do, or when a better functionality or performance is possible. In most of the existing solutions, the adaptation processes are assigned to an external adaptation manager. Often, the system developers are responsible for the system adaptation as well. Just consider, for instance, how the Windows environment using the backdoor strategy is time to time updated. But nevertheless, this adaptation manager is typically separate from the application system and its logic. Adaptation mechanism implements several processes, for instance, monitoring system entities and the environment, analyzing significant changes, planning how to react, and executing the decisions to take effect. A self-adaptive system evaluates its own behavior and changes its own performance. If we look into the complexity of self-adaptation, then first of all, we have to state that there are multiple perspectives on system adaptation. I just collected 13 most important ones. For instance, causes of adaptation, or the operationalization strategy of the adaptation, then the criteria and the triggers of adaptation, then the resource management issue related to adaptation, the target of the adaptation and what can be set as a target, the time of planning, then the distribution of the adaptation between the agent in the system, then the subject of adaptation, the arrangement of control, frequency and duration, control methods, control theoretical fundamentals, and finally introducing the adaptation. So we are facing a quite complex problem, as you can see here, based on the different subdomains, and this partially explains why we don't have complete or at least sufficient solutions for it. Let's talk about the reasons for adaptation. 4 sources of the need for adaptation have been identified. First of all, it is problematic to foresee all requirements in the design stage because of the broadening and complexification of using such systems in society. The second is that it is difficult to predefine all system operation and interaction modes owing to the growing uncertainties concerning applications and stakeholders. The third one is that as a consequence of the unpredictable incidental effects and changes in the environment, it is difficult to establish overall resilience in the design phase. And the fourth one is that owing to the emerging new technological services and experiential affordances, it is often possible to achieve a better performance than the one which was programmed for the system. System adaptation is a systematic procedure. It cannot be improvised or just done heuristically. There are certain principles what are to be taken into consideration at developing a system adaptation. First of all, self-adaptation should be seen as the capability of a system to adjust its behavior in response to the changes of the environment. Thus, if we look at the first part of the first phrase, the self prefix here indicates that the system autonomously decides, that means with minimal or no interference with humans, how to adopt or to organize themselves. Systems can variously accommodate changes in their context and environment. Some self-adaptive systems may be able to shift objectives and change functions even without any human intervention. For many years, guidance is useful in the form of higher level objectives. For instance, if the system can get additional knowledge to explain situation or to embody new concepts through, for instance, ontology. Providing, removing, and integrating resources to enable adaptation are still unresolved or just partially resolved issues in the physical realm, while some remarkable progress has been achieved in the software realm. If we look at adaptation from a control theoretical perspective, then we can consider the following things. The literature, first of all, distinguishes between conventional control-based adaptation, proportional integrative derivative PID type, or state representation-driven type of adaptation. The literature also identifies so-called advanced or sophisticated control-based adaptation, model predictive, optimization-based, or stochastic approach. And the third category is the so-called knowledge-based control, when rule bases are considered, fuzzy representations are considered, heuristic approach values, or analogical reasoning is applied. And the fourth category is the inferring and reasoning-enabled control, which is data-driven or can be learning-based, adaptive, prognostic, and twin-based mechanisms. These type of adaptations apply to complex software systems rather than to resource heterogeneous cyber physical systems. So some of the hardware adaptation, hardware change issues are not yet covered. In line with the current layering of ICT information and communication technology systems, the categories of infrastructural resource adaptation, hardware and software adaptation, reuse middleware adaptation or reusable middleware adaptation, and domain-specific application software adaptation have been differentiated and applied. The software self-adaptation happens in multiple dimensions. This figure tries to explain what might change. First of all, we can consider the data which is processed by a particular algorithm or a whole software program. It can be variable or can be static. At the same time, the code used at programming the algorithm can be also static or variable. So in the case of software self-adaptation, we can define based on these descriptors 4 domains. And the first one, where both the data and the code is static, that is a monomorphic software engine, which means that the software appears just in one particular dedicated form. When the data are variable, then we can talk about generative software engine or software programs or mechanisms. When the data is static, however, it is approached with differently programmed mechanisms, then we can talk about virtual software engine. And then when both the data and the code is variable, then we are talking about polymorphic software engine. So this figure somewhat underlines what I told you, that some insights and useful progresses have been made in the field of software adaptation, and similars can be expected for the whole heterogeneous systems, in particular for the physical part for it. So why to deal with system adaptation? Why is it so important in the context of cyber physical systems? First of all, it has to be in our mind that the operational environment of most of the smart cyber physical systems, as well as the operational state, may dynamically change over time. Then, full anticipation of the environmental changes, as it was briefly remarked earlier, at the system design time is challenging or often even impossible. The operational goals can also be changed and or optimized, and failures can be avoided or corrected or should be corrected. These raise the need for the potential of runtime adaptation, RPA, is often used abbreviation. RPA of cyber physical system is self-adaptation, and it cannot be externally stipulated or enabled. This may concern the runtime behaviors and structures of the system or both. Later on, you will see that different forms of adaptation can be achieved with the various generations of cyber-physical systems. And here is actually the explanation for that. We were talking about first generation cyber-physical system. In the case of this generation of systems, there is an initial system space, a kind of problem space, what they have been developed for. And obviously, it can be stretched, which results in the system space. Typically, the initial system space is just a subset of the possible system space. But what is important here that there is a particular operation state which can be tuned to a different, sorry, so there are multiple operation states and there is a designed operation state. When the system tunes itself, it goes to a different operational state, which can be considered the operational state. If we look at second generation cyber-physical systems, they are doing much more. They also have an initial system space, what they address. Obviously, what these adaptive systems can do, they can extend their system space. So they can extend the space of the solvable problems because they can pick up new operational features. And then if we have a particular designed operation state, it might go to a newly defined extended system space where it may find a better or even optimal or a operation space. If the system adopts itself multiple times, it may find different optimal operation states on the extended system space, but it cannot go beyond that. If we consider the third generation cyber-physical systems, which are evolving systems, obviously they are also designed for a initial system problem-solving space. And there is a characteristic design operation state related to that. They can extend their operation space multiple times. And they can use, like in the case of the previous the adaptive system, they can use the extended system space to find solutions. However, due to the evolution, having new resources, new capabilities, they can extend the system, the operational space, with new space elements, space components. So it means that the actual operational space for the evolving system after or in a particular stage of the evolution will be the union of all the spaces. So the system can jump from one extension to the next to find the best. And if it is still a suboptimum, they can go on with the process. And this is the essence of the evolution, and this is why we can say that the evolutionary system can be assumed to set new operational objectives, new operational goals, to acquire new resources, because they know, in a sense, based on the historical trend, where to go. And now let's look into what might be expected from the fourth generation cyber-physical systems, which obviously can have a kind of reproductive capability. So again, they have a design operational space and they reproduce the system operation space in a form which is not overlapping with the initial one. They can do it multiple times actually, and then they can find the problem solution with their replicas. And every replica may have the same operational characteristics as in terms of their handling than the original or initial system state. So these are the differences. I hope I could explain it to you sufficiently, and now you can see that what the different adaptation capabilities mean. So if we typify adaptation, first of all, we have to start out from the criteria of what might trigger the adaptation. It can be, for instance, goal-related need for adaptation, task-oriented need for adaptation, or performance-related need for adaptation. So with regards to the occurrence of the change in the process of the system of operation, adaptation can be proactive, which means that before actions are before negative actions are happening, or it can be active, monitoring the procedure, or it can be reactive. When something happens, then the system is adopted. An innate uncertainty is related to the prediction of the change and the needed adaptation in advance. So this is why proactive or predictive adaptations are still challenging. Probabilistic and statistical models, PMC or SMC, have been used in proactive adaptation checking. Probabilistic methods is not appropriate for large, complex self-adaptive system models due to the state explosion problem. PMC is costly in time and may suffer from memory constraints. So if we are talking about the procedure within the system towards adaptation, it can be described by this particular model. So first of all, we have to assume that the objectives of operation and the conditions of operations in one way or other are defined. We have to assume that there is a non-steady state in the application environment and everything is triggered from that. We can assume that the system, both the physical constituents and the cyber constituents do their operation, and the states of the system operation are known. Then the whole process, what is implemented for the operation, starts with the sensing in dynamic context. Then streaming of massive data is happening. And then based on the sensed content, situation awareness is formed. And based on that, and using some sort of causal or imperative reasoning, actually a planning is done, which is considering both the operation and the architecture of the system. The need for the adaptation is learned on system level and it is operationalized on system level, and this is how we get to a kind of proactive self-adaptation. Easy to describe as a simple procedure, but much more challenging to implement it on the floor. Then the next topic is the different concerns of cyber-physical system adaptation. Here is a figure which shows the complexity. So for instance, if you start out from the sort of next generation cyber-physical systems, then we have system-related concerns of adaptation. We have software-related concerns. We have hardware-related concerns, and we have cyberware-related concerns. This is what I can suggest you for research, for instance, as general topic. First of all, the overall system concern. So what adaptation means on system level, this is a kind of starting point. Then anything which is related to hardware management concerns, because for instance, a simple example, if a new hardware would be needed for a particular different type, more modified type of operation, how to provide it. It is not necessary that a part can deliver it or not something that you can retrieve, for instance, from the internet. So what is with the hardware management? It is still an issue. Then the cyber management is also problematic because the cyber content at this very moment is not completely, not exhaustively known, and therefore there are many white spots. Then the system supervision concerns, supervisory concerns are also a remarkable group. And then, for instance, the software dependability concerns. When you change, when you adopt the system, how about the dependability? When you can be sure that the system does what it is supposed to do. And the system modeling concerns, if the adaptation is taking place, how can you change initial models? What does it mean to develop runtime adaptation models, and how to change adaptation models actually in harmony with the control models or even with the system model. And then the sort of self-evolution concerns, which will be very soon addressed. So this is the complexity what I'm talking about. This is what we have to consider, and we are precisely on time for the suggested literature. I would like to call your attention, please, to a paper what I published with Professor Kalchar, a review on the principles of designing smart cyber-physical systems for runtime adaptation. Actually, very recently, we edited a special issue for a journal, and we also addressed the issue of runtime adaptation, but in combination with the runtime evolution. Then the second paper what I recommend is about the feedback control as a MAPE-K loop in autonomic computing. It will be addressed very soon. I mean the MAPE loop. Then the third paper is about reliable composition of MAPE-K loops in self-adaptive software systems. A lot of original ideas are in this paper. And then the next one is about a comprehensive technological survey on the dependable self-management cyber-physical system. So how to make the adapting system, the self-adapted system dependable. And the last one, what I suggest for you to look into or even study deeper is entitled Enabling Self-Adaptive Workflows for Cyber-Physical Systems. That concludes the first block. I stop sharing. I come back to the panel, and I would be pleased if you could comment, if you could pose a question. I don't see any question, if I'm right, and please, Professor Kang, correct me. I cannot see any question in the chat box at this very moment. So, colleague, the floor is yours.
Any question, participant? Any question?
Seemingly, we don't have questions. And then, as the Latin says, why to speak when no one listens? Let's go further and let's start the presentation of the second block. I share the screen again. Please kindly confirm if you can see the screen. Can you?
Yeah, it's coming, yeah.
Excellent. And obviously we continue with the recording. So the second block is about managing adaptation to, or from managing adaptation to managing evolution. So adaptation management actually a complex system, a complex issue, which includes developer, the system itself, and both. So there are different alternatives for managing adaptation according to which stakeholder we consider individually or together. The other aspect of talking about adaptation management is to consider the time when the preparation for the adaptation is happening. It can be first of all, in the development phase, and it can be in the operation phase as well. So this way, if we combine the stakeholder with the stage of managing adaptation, we will receive actually a matrix. And this matrix includes the following fields. First of all, when we consider the developer and the development phase, then the developers can decide in this phase on all process adaptation and needed resources. But there comes the problem what I already sketched up, namely that how much we can foresee, how much can we specify in the development, in the design phase. So the developer cannot do everything. Then please consider that we are in the development phase. So it means the system is not there because we are just designing. So the system cannot do anything with its own adaptation in the development phase. And based on this reason, we can say that even they collaboratively cannot do anything with regards to managing the adaptation. And then consider the next stage, the operation phase. Obviously, as much as developers are considered, they can initiate some adaptation and provide the needed resources for the adaptation. It means a kind of collaborative supervising by the developer in the operation phase. Some cases it can be so, in some cases not, especially when the system operation is very lengthy and very complicated. So then the next thing is obviously that we consider a kind of developer system coalition for the managing of the adaptation. It means that in principle we can develop systems which ask the designers at runtime to adapt in context and integrate resources. So actually, it's a kind of task sharing between the system and the developer. Here, the system should be able to do self-reflection and should be able to communicate with the developer. And obviously, what I said earlier with regards to this particular sort, it applies here. And then comes the next one, when the system is managing the adaptation in the operation phase. It means that the system should have some capabilities, initial capabilities from the development phase to manage it, not knowing what it is, but these capabilities which are built in as tools, as resources, should facilitate that the system decides on adaptation and acquires and integrates the needed resources. So this is what we can consider here as a basis. When we are making decisions on managing the adaptation of cyber-physical systems, obviously the generations, as I explained earlier, takes a important role there, but also the issue is for the implementation that how can a smart cyber-physical system safeguard the dependability after the self-adaptation or runtime? Many things should be done. I will give you a summary on this issue. And this is what I mentioned. In the development phase, the system itself is not there. But another approach is, can we learn something from other systems and to operationalize in the case of a new system? This is a research issue at this very moment. There are colleagues who are really doing intensive and deep going research in this particular field. So after this overview of the opportunities of adaptation control, let's talk about a kind of typical approach for managing the adaptation by the system themselves, which is bringing in the concept of the MAPE-X loops. It is actually a very transparent, a very simple structure, conceptually, completely different issue, how can we implement it? Because it assumes that there is a target variable system. This system is monitored. We already know how it can be monitored. The monitored information is analyzed, and then a plan is developed. And this plan is executed, and as a result of the execution, the target variable system is modified. It can be purely data-based, but there is an opportunity to support it with knowledge. And the knowledge can be obviously used in the system itself, but in all stages in the monitoring, the analyzing, the planning, and the execution phase. Now, obviously, you can see that the MAPE is actually the acronym formed by the first letters of the verb, and the X can be knowledge, but also can be organization or operation, and so on and so on. These can be facilitators for the implementation of a MAPE loop. Let's see how this loop is operationalized and how can we operationalize it. As I mentioned, it involves monitoring, analyzing, planning, and execution. The monitoring should be decomposed to activities like the goal specification, identification of the system requirements, the sensors application, and the data collection action. The analysis, it can or should, better to say, extend to data mining, then the model building and the model updating, then to a reflection on the requirements. It should include also reasoning with uncertainties, pattern analysis, and situational inference. The planning is likewise a complex activity. It includes, for instance, making stochastic estimations, forecasting simulation, performance optimization, neural pattern extraction, finite element analysis, or even abductive reasoning about how to develop the optimum plan. Then the execution phase or the execution operation includes something like state description, information reporting, system reconfiguration, better to say, and effector management. So these are the sub-activities. And then process-wide, we can create then a standard model of self-adaptation using these things. We start out from the managed resources, and on the other hand, we have the autonomic manager of the self-adaptation. The process starts with the sensors. The sensor information is forwarded after purification and structuring to the models, which are reflecting on the system state. The models can be knowledge intensive, so knowledge can be added. And then the monitoring goes to the M part of the MAPE. When the monitoring is going, the analysis is taken place and the different situations, the different states are evaluated. Based on the evaluation, a requirement for the adaptation is formulated. The requirements are converted into change plan, which goes into the planning stage of the MAPE model, and then the plan is operationalized, it is executed, and the execution obviously concerns the model, but it goes back also to the managed system resources and, for instance, causes a chain. So this is how it is. This is what we have to consider if we want to implement system self-adaptation in the past. But obviously, I was talking about the need for testing the adaptation, because the contrary to the fact that a particular system has been adopted, it should be reliable, it should be dependable, and it shouldn't go into on wishful states and situations. So we have to talk about the general mechanism of testing self-adaptation. And this procedure, namely the testing process, is actually synergistically integrated into the operation process of self-adaptive system. It has multiple stages and multiple aspects. First of all, one aspect is setting the objectives of the system run at runtime, and the second major aspect is the resource management at runtime. I mentioned that we can in principle manage cyber content well. We have advanced solutions already for software resource management, but the hardware system management and the complete heterogeneous system management as a whole is still lacking behind. So again, there is a loop integrated into the operation process of the system. Based on this, the plan is defined and tested. Then there is a need for verify the change. So if you have a plan, the first thing is to see that if it is logical, if there is no logical error in the change plan. And obviously the second one, what is also important to verify, if the change, what is implied, is feasible. Because if the plan is illogical or infeasible, in that case, the verification has already a important finding that we cannot go further with the procedure. Let's suppose that the plan went through the verification filter and the process can go on, because actually, if not, in that case, you can generate a new plan and to go further with it. So when the change is operationalized, then comes a next phase, which is the validation of the change. So if the change is feasible, then here it has to be seen if the changing achieves its goal. So if new objectives have been set for the system, then are they met? Are they fulfilled? If not, obviously, we have to go back to the plan and or the planning and have to change the plan. So only in that case, if the validation provides, the runtime validation provides a negative result, then can the system operation maintain, and that particular change system operation should be accepted or can be then accepted as reliable or dependable. This is, again, a very simple overview of what we should do. But the implementation, even if we have the make model, is not so important, because actually everything on what I was talking about are deficits of the current make model, because it is not putting enough attention on the verification and the validation aspect. So far, so good, but let's go further. And obviously, the time is also running fast, so maybe I just mention there are various schemes in the literature developed, and you can find them, for instance, for probabilistic model checking and developing adaptation tactics and also, for instance, the statistical model checking is an important aspect, but I have to tell you that it's somewhat lagging behind the opportunities provided by probabilities approach for the reason that here the statistical simulation leaves the system itself as a kind of black box and approach it from outside just based on what sort of output has been generated. So it means that the goodness of the verification results depends on the quality of what sort of statistical model is used here. So there are good examples for them, an SMC algorithm statistical, for instance, the simple Monte Carlo simulation approach, the single sampling plan approach, or the sequential probability ratio test. These are the three most often used statistical model checking approaches. Here, a different figure, maybe I will not be able to go into the details with a view to the passing of the time, because I also would like to elaborate on the evolution issue, but you can study it later on and you can see how we can end up with specific optimal or executable adaptation tactics. And I mentioned that evolution is coming now, and this is an important aspect in the transition from second generation to third generation, and handling the evolution problem in the case of third generation cyber physical system, at least as important as handling the cognizance and increasing the understanding level of the system. But actually, maybe this level, what I mentioned, namely the higher level of cognizance, will contribute to the evolution of these systems or evolution opportunities of these systems as well. But let's look into what evolution actually does mean and how we can treat it. So you have seen earlier in that sort of 4-block figure that adaptive cyber physical systems are designed to work in a definitive operational domain within a constrained operational domain of VSC. The conditions the systems are intended to operate under are well defined and can be inferred from past operations. Evolution happens when the operational domain and the innate ability of change of a system are extended. I explained it to you, multiple problem solving domains were defined in the case of the evolutionary systems, and from one operational domain the system could shift to another one, and so on and so on. So this extension of the operational space can be realized in multiple ways depending on many factors. For instance, the objective of the system, the performance expectations of the system, and the adaptation opportunities of the system. It usually needs additional system resources. It's almost obvious that are directly available or are to be provided. The second is typically the case because all the resources for unpredictable system changes cannot be availed in the system. So this is a major difference, namely the the management of additional system resources is a major difference compared to how we can handle an externally adapted system. So let's talk about the additional elements of the concept of system evolution. Because system evolution implies the need for sophisticated resource generation and also for the resource management, what I mentioned just before. Resource generation relies on humans that produce and add new computing elements to the system. It is not assumed in the evolving system concept that the system in itself can figure out what sort of new resources are needed, although, as I said, if the cognizance level, if the understanding level of the system grows, then it might create opportunities. This is in infancy with regards to the research what has been invested so far. So these elements must be integrated into a system and then deployed runtime. Resource generation can only be partially automated, whereas the resource management is supposed to be increasingly automated process. So often called evolution engine, those sort of change mechanisms which are facilitate the system evolution can operate on runtime models. But the runtime models are supposed to describe explicitly the goals and the operations, the architecture of the system, what is operated on, and the lifetime changes anticipated in the design time. So the evolution engine actually can be implemented in a kind of exploratory mechanism. For instance, the evolution engine can run experiments in a sandbox and changes the system model until it satisfies the new condition. During this, the evolution engine integrates new computing elements from the resource warehouses as needed. Obviously, here the computing elements, mainly hardware and cyberware elements. The resource developers, on the other hand, can place new computing elements and their specifications in the resource warehouses. The resource warehouses provide machine processable specification and or procedures for autonomous incorporation by the evolution engine. Self-evolutionary side of the systems reduce the human role. As you can see, everything is here going toward automation. So the self-evolutionary side of the physical system reduce the human role in supervision, but count on this sort of human contribution and cooperation in the resource generation. Uncertainty of evolutionary RGs and interoperability, the resource generators, and interoperability of the extended systems are the major unresolved issues nowadays. So the next topic what I would like to address is enabling self-evolution. So let's start out from the statement that self-evolving cyber-physical systems focus on the recently proposed paradigm of lifelong computing. They are also driven by the idea of self-growing software and knowledge-growing systems. While runtime handling of software and cyberware elements is feasible, the same of hardware is challenging, and this is something what we really have to focus on. This opens the door to self-manufacturing, for instance, rapid prototyping, but also to the issue of material handling. Because if you want to provide the physical hardware, then somehow the system may be able to self-manufacture these, but also there is a material handling kind of issue. We have to deliver, for instance, those sort of resources which are needed by the system to where the system is working, and it is especially complicated in the case of a worldwide distributed system, for instance. Software evolution was considered automated was considerably automated in the past decade. Just consider that what happens with high-end web applications and, for instance, with operation systems, but it remains still a human-driven activity. These open issues of handling both anticipated and unanticipated changes point at the need for new paradigms, which are at this very moment not yet documented in the literature. I don't dare to say that some researchers are not thinking and talking about them, but I haven't seen any serious comprehensive study in this field at this very moment. So therefore, what I can summarize here, coming to the end of this blog, what sort of research issues we might address and tackle. For instance, concerns of dealing with system self-evolutions can be formulated as hypotheses as follows. Understanding and modeling self-evolutionary systems. Understanding how they work, what is the optimal operation for them, and modeling. What sort of models they need, how to model them, how to change their models. Then development and application of dynamic programming methodologies. Current programming environment are not the optimum with regards to system adaptation, not to mention system evolutionary issues. So definitely new tools for dynamic programming will be needed. And then designing reliable functional evolution mechanisms. Also designing robust architectural evolution mechanisms is a task. Then recognizing and handling emergent affordances. So if the system operates, what sort of new affordances are out there? What can we pick up? What can we operationalize? And then related strongly or closely related issues that capturing and treating emergent situations in which, for instance, new affordances may appear. And then changing the adaptation logic of the system and supervising it at runtime. And very briefly last time I was talking about the product functional capabilities which complement the normal functional capabilities. What does it mean to address parafunctional capabilities in the case of self-evolution mechanism? A practically virgin field for further study. So please consider this. And taking care of the overall just-in-time resource management. So why I did it, why I presented this list. My consideration was that most probably there are people who are listening to this presentation who are coaching PhD projects related to smart and next generation cyber-physical system. They may initiate this, but also the PhD students who are looking for really meaningful PhD topics in the field of cyber-physical system can work on it, and I guarantee that the papers which are published in this particular field will be accepted for publication if they represent a reasonable high quality, because the topic is just looked for by all publishers. So self-evolving cyber physical systems can be diagrammed like this. So the computer think system in itself adopts. And then we have the already discussed evolutionary engine, which works with the observations and feeds back to the whole system and consider all the opportunities for the evolution, and that is transferred into the system. So the evolutionary engine uses a self-replication and also uses the mean as a means a computing warehouse where the different type of resources are placed. And obviously this warehouse should be externally fed with new resources which should be produced by human experts. So if we want to go further with this issue, then we can typify emergence in systems And we can say that in conventional systems, actually, very low or no emergence is concerned, but in the next generation, and especially the AI-enabled system, a relatively high level of emergence should be taken into consideration. I unfortunately don't have time for a movie, but because I have to wrap up this blog, and I want to summarize the novel requirements for the future. For instance, the monitoring human, social, business, technological, and industrial trends in a holistic framework, bringing social demand and technological affordances together into a triggering relationship, conceptualization of smart architectural systems and services in socialized and personalized application context, and to develop and apply purposeful reasoning and learning mechanisms for aware and adaptive systems and services, and apply data analytics and forecasting methods to predict expected behavior, use, misuse of products and services. So at the end of this blog, I would like to spend a minute on mentioning five or so papers which I suggest for further study. The first one is entitled Towards a Mega Model to Model Software Evolution Through Transformation. Here, the mega model concept is something which is novel and new. The second paper is about performance evaluation, matrix visualization, performance variations along software versions. Very good paper for software developers. Then the next paper is formal approach for managing component-based architecture evolution. Then the next one is model evolution by runtime parameter adaptation, and the last one is runtime evolution of the adaptation logic in self-adaptive systems. So this was the first lecture today. We have to conclude now. I apologize for the delay. The first block introduced the forms and methods of system adaptation. The second block discussed the concerns from moving from adaptation to evolution and handling the evolution in systems. I will continue. There will be two more blocks presented after the break. I stop sharing now and come back to the mosaic. If you have any question, comment, please put aside, and perhaps we will have time, at least 10 minutes for the break. Thank you so much for your kind attention.
Any question?
I guess Dr. Vasanta has a question for me.
Yeah, Vivek.
Yes, sir. Yes.
Oh, good.
Just a basic curious question actually. As a evolving system, is it necessary to have a fully self-evolution system, or there can be a man-in-loop for the cyber-physical system? If you talk about self-evolution cyber-physical system.
The sound was very much broken again. So what I could understand was the following. So you were asking me about the evolutionary aspect of cyber physical systems. And the question was about, please be so kind to repeat it.
Yes, sir. I am asking that is it important that the system should be fully self-evolving, or there can be an involvement of human in the loop?
Oh, wonderful question. Wonderful question, because it has two aspects. And thank you for using the mic. Now it was much clearer than earlier. So the first question is, I believe the best for us as scientists, as researchers, as we see the evolving cyber physical system as possibility. not only for study, not only for academic study, but also for industrial implementation. There is an acceleration here. So actually from the very simple plant type cyber physical system, within 10, 15 years, we reach to the domain of smart cyber physical system, second generation system. If the acceleration goes on, obviously we can be in the field of the evolving cyber physical system domain. But please see, there is one thing which is a kind of break, because the opportunities are creating a kind of acceleration. But on the other hand, there is a break, and the break is coming from the complexity, the exponentially growing complexity of the problem. So it means that we haven't exhausted at this very moment the first generation cyber physical system content, because these systems are working very well and they need further studies, and they will be with us because we don't leave all of them behind. But obviously the second generation smart cyber physical system can come out from the industrial application context. They can be plant type of systems, and we can use them in, for instance, in the automotive industry, in the medical industry, you name it. But what is interesting that the second generation cyber physical system is parallel studied with the first one, and this is already starting with the third generation. But these processes are slowing down because we need to have a lot of research and lot of experimental development to understand what adaptation means. And also, we need even more efforts to understand what evolution means. So this is what I believe the best way of seeing the current development. What is interesting for the time being for you to tell, and this is my opinion, and maybe somewhere there is someone who doesn't share this opinion, but according to my view, is apart from the software arena, where adaptive software and evolutionary software implementation is intensively studied. For instance, one of my acquaintance or even friend in Belgium at the Catholic University of Leuven, he has a group who studies, for instance, the evolutionary opportunities of software systems. And for instance, in that special issue, which comes out in the Journal of Information and Process Science in Design, sorry for that, in this special issue, they published a really top-edge paper, on this work. But it is a new opportunity for the academia, because the academia should be ready when the industry needs this sort of knowledge, and also this is something what we don't know exactly how will manifest in the future. The complexity doesn't allow us to see clearly, although we see that the path is like this, that from smart systems we go to cognizant systems and self-evolving systems, but we don't know enough about to correctly position them. That's how I see. And this is why I always skeptic, when people who are actually having a very distant view of AI, they are already talking about intelligent systems or whatever. For me, simply the cognizant system and evolving system is such a mind-blowing activity, that it would need another 40 years research from me. So hope I see on your face that how to say, you followed my explanation, and I have to return it with a big thank you because again, wonderful question. Thank you so much, and really exciting. And it shows me that you deeply follow and understand these sort of things. Thank you so much, sir. Really, thank you so much.
Thank you.
Professor Tandon, we discussed this particular thing, and how about keeping a break? Or you are already taking the break? Professor Tandon. You have a task to do before the break.
Okay, so if no more question, again, we are not left with much time, but 5 minutes, we can take a break of 5 minutes, or you want more, 10 minutes?
Will you take a photo?
Sorry? Yeah, I'll take photo also, but you let me know the time.
Okay.
Okay, please switch on your cameras.
This is what I thought of.
For the group photo. All of you, please switch on your camera. Mandloye and Ashish Gupta. He seems to be missing. Yeah, what? Just 1 second. I have not opened. Okay, so just one more photograph. Prashant, your face is coming very black. Can you please, can you move our lights better now? Mandloy, you're still missing. I think everybody else is present. So we'll mark you absent. And all of you smile, please. Okay, so we'll take a short break now, and we'll reassemble in another 8 minutes.
Yes,
So
excellent.
Indian time 3:20 we'll meet over here, and we'll listen to the concluding lecture of Professor Imre Howard.
Exactly. And don't go away because there will be two more fascinating topics discussed. Thank you so much.
If we go away, we can prepone quiz also.
Yeah.
To know this thing actually. Okay, so maybe 8 minutes up from now.
I'm ready to start. Okay, let's get started. This is the last presentation in the course. Actually, the 20th lecture, which will include 2 blocks. And these blocks will be about understanding interactions and the concepts of digital twins, which are somewhat interrelated in cyber-physical system context. So the first block is about new challenges of interaction with cyber-physical systems. Why this topic is interaction? Why we have to deal with it? Just see this interaction, human system interaction, when we are talking about automation like here in the automotive industry. Interaction in this environment when the production is done automatically. Interaction here when robots are the bosses and they are taking the role. So what are we talking about? What is the role of interaction in the context of next generation cyber physical systems? Obviously, what we have to consider is the content of several former presentations. We are aware of the fact that the cyber-physical system paradigms are shifting. We are also aware of the fact that implementation of smart reasoning and behavior is going on. We know that we have to count on the adaptation of systems, runtime, even count on self-adaptation. And then what we can expect in the future, systems in multiple forms. Polymorphism and polymorphic system physical, cyber physical systems will be dominating. And then, obviously, there will be a completely different state of knowing and doing when we have high-level progression in these domains. But this holistic view will allow us to make findings, reflections, and implications. The problem at this very moment that everything is premature. So it's really not easy to forecast the future of human system interaction beyond the changes of the role which comes upfront later on in my presentation. So this is the big question mark for the time being. How can we have a holistic view on interaction with cyber physical systems which are even evolving. We have to see what happened in the past and especially what happened in the last couple of years, because recently there is a radical change with regards to interaction. So the overall complexity of the cyber-physical system is rapidly growing. The systems are becoming intellectualized on a high level. Human roles are changing from direct controllers to remote supervisors. The offerings of many systems are orientated to services or to experiences. Automation of the system is growing due to the applied artificial intelligence. Stricter regulations for environment protection, safety, reliable, and social responsibility are coming out every day. And then all these together obviously will influence the interaction with current and near future cyber physical system, but precisely how? That's the major issue, and this is what I would like to give some aspects. Let's start out from the so-called realms of interaction, because in the relationship of human and system, we can have a kind of universe of discourse where we can place current development. So actually, what is important in this setup, that in the human system relationship, who is taking the initiative to achieve a objective, or who is taking the initiative for certain kind of interaction. And why traditionally it was related to human. So we were talking about human interaction and the dominance of it when the human used tools, low complexity systems. Then when human used systems, then we are talking about human system interaction, because even if the system was there, the human had to put it into operation, should control it and supervise it. But here is the change. Actually, we can talk about system-human interaction. Understanding is very easy. Just consider, for instance, home care. Home care, we can have service robots. Now consider that there is a smart robot out there which recognizes that the tenant, the patient, or whatever has fallen. Obviously, it has to conclude that it should go there to help to put into a standing position or to put into the chair. In this case, the system decides. So the system makes the initiative to do something, and in that case, the human will be just a kind of passive element of the interaction. But obviously, it is not 1 and 0, but because there are situations where it is much more balanced, but for the favor of systems typically. And obviously, when we are talking about system of system structures and arrangement, we can talk about system-system interaction as well, which in a sense might mimic what happened with the human-human type of interaction, but maybe other forms which are not known yet may be discovered or developed. So if we can accept the starting point that we have to be prepared for the stage where systems can also make initiative for interaction, then immediately we have to see that what sort of dimensions are out there for the human system or system-human interaction. So the interaction actually has 5 dimensions. One is the task of interaction. So what is the subject of the interaction? And this is a kind of, or boils down to a task management. Then the second issue is the domains of interaction. The third one is the modalities of interaction. The fourth one, the context of interaction. And then the last one is the levels of interaction. And obviously, they are not completely independent. There are interdependencies between them, and what connects them is the task. Because the task implies a domain of interaction, it defines certain modalities, it specifies the context what are to be taken into consideration, and it also permits or not particular level of interaction. So this is a simple reasoning model about the dimension of human system or system-human interaction. In the rest of the presentation, I would like to briefly elaborate on all the five issues. What does it mean? What we as cyber-physical system integrators should take into consideration. I have to start out what we already have discussed, that the human involvement in cyber-physical system can be discussed according to four roles, according to the played roles, according to the intentionality of the human involvement, the competencies, and the responsibility. In terms of the played roles, we said that service customer, system contributor, input provider can be, and for each of them, some further specifications can be made. With regards to the intentionality, cooperative, neutral, or adversarial can be identified. With regards to the responsibility, accountable or unaccountable responsibility can be considered. And finally, the competencies can be specialist, knowledgeable, or just informed. This is what we can assume actually on the human side when we designing interaction. And then when we do it, we have to face a couple of challenges. For instance, intellectualization, socialization, and personalization changes human relationships significantly to cyber-physical systems. Interaction with socially deeply embedded and behaviorally personalized cyber-physical system is becoming more articulated. So in the human and social context, when the cyber-physical, smart cyber-physical systems are applied in these fields, they are socially deeply embedded and behaviorally personalized. These are new elements, new factors. Simultaneously, the old forms and means of direct interaction with the systems may be reduced in terms of their influence or even may become obsolete. New theoretical and methodological issues of cognitive interaction are also needed and pursued. Quality expectations, for instance, transparency, safety, satisfaction, and so on, are high. And new interaction and collaboration frameworks are strongly needed. For instance, the co-voting. It means in the interaction with robotic, multiple robotic devices concurrently. So I mentioned that everything starts with the task, and we have to understand the tasks which are handled in the interaction and in the system operation correctly. That's the reason why there is a need for conceptualization of the task and for the development of a task framework. I must tell you that rather complicated task structures were proposed. Here I would like to show you a simple one, which is obviously not good for everything, but at least good as a starting point. So the task obviously is adjusted to a autonomy level. The task requires a particular human profile. The task has preconditions based on which it can be completed and solved. The task is composed of different or the task execution needs different activities and which should be clearly defined. then the task should fulfill and the execution of the task should fulfill certain type of constraints, and it is associated with a kind of fallback plan. So what if it what we are failing? Then, if we want to use this simple task framework, then we have to further articulate the preconditions, because that includes, for instance, opportunities, willingness, and capacities to do something. And also the activities need further articulation, because they include, for instance, definitive action, or intended action, constraint for the actions, or the previously mentioned elements of the fallback plan. So this is a simple approach for the conceptualization of the task. And when we are designing a smart cyber-physical system, and when we want to make decisions on the interactions, I suggest you to make the task mapping with regards to the human and the system, and make a decision which tasks are allocated to the human and which are supported with some sort of in quote automation by the system. Also, for instance, in the case of the activities, you should include the initiatives, for instance, and the essential level what is needed for the execution of the activity. So the next thing is obviously to arrange the task flow, and it is a scenario-based activity in the case of a smart cyber-physical system. So in a kind of scenario building, the following task flows, processes, and activities should be considered. First of all, the operation process of the cyber-physical system. Then the cognitive and motor actions of the stakeholders, the user. Third, the interaction of the stakeholders with the system. The and obviously the stakeholders can interact with each other. That's why I put the users into brackets. And then implementation of the procedures of services, and also interoperation procedures with other systems. So the main issues are how to construct and analyze formal process models, and then what media to use for presenting the process. So if we go to the process representation, actually it can be done very simply and very effectively. And this is what I several times practice with the students, PhD students or graduating students, and we achieved quite reasonable results. Because, for instance, the considered or the to be considered real-life processes can be in fact modeled by formal process scenarios. For instance, if we can have a starting protocol, or we can develop a protocol for the action. And obviously, this protocol is the basis of the protocol is action and time, and their logical sequence. So it forms a kind of tentative or imaginary scenario, which then should be put into implementation context, not only activity point of view, but also from the temporal aspect, how things and when things follow each other. So here is, for instance, what a simple process representation means. You have to create a scenario for the sub-processes of the system operation, first of all. Then you have to identify the needed sub-processes of human perception, cognition, and action. Then you have to identify those sort of cooperative processes, in sub-processes, in fact, in which the human interacts with the system, or the system interacts with the human. And then you have to also consider those sort of service processes which are providing the output of the system, the service implementation, which can be obviously with or without the involvement of human. Now, if we have this, then we can start out from the human activities and we can project these activities, for instance, to the sub-processes of the system operations. We can create a relationship between these two streams of activities, namely the human activities and the system activities through the interaction flow. And this is how we can couple. Then, based on the interaction, the system receives, for instance, data or commands to fulfill something, and then it may go to the service process, and the result of these system activities appears in the service implementation sub-process. Then through the interaction process, the completion of the task in the service division, service provision in the sub-process can be monitored, and through certain kind of interface, connection can be made with the human, who in the meantime, as you can see here, is involved in perception or cognitive or whatever other motor process. Then we can go back again when a decision is made by the user to the sub-process of the system operations, and then if there is a result, fungible result, then it will appear in the servicing process, and this way we can go further and build up a complete interaction process. So it is a kind of sequence diagram, because there is a timing, and you can allocate to these sort of dots which are here time point, and then you can define precedences or subsequences with this model. But the major issue is, and the major difference from with regards to a sequence diagram, that here the four types of operations are more deeply and more articulately considered. So this is what the flow charting tool, what we have several times used, and actually there are some concrete computer tools which could be used for this particular purpose. We used ONMA. The mathematical process modeling tools were facilitated the time process simulation, for instance, in our case, because when it was built up, actually we always tested the properness of the scenario logically and time-wise. But obviously, we don't have to forget that the system automation is around the corner, and there are changes, as was briefly summarized earlier, in terms of the role of the human being, and also there is a role change with regards to the system. So the direct performer region, when the system is not considered for automation, human execute the necessary operation, control is provided predominantly by the human, and the human-human interaction happening only. This is actually the past. What we have nowadays is that the user is in the direct controller position, and take this region of this screen. And then human presents limited the system presents limited automation. The human closes the loop of the operation, and the human performs control over system action. And human system interaction with regards to the initiative is typical. Then in the third stage, when the supervisory controller position is to be taken into consideration, then the system is largely used for automation. Human and system closes loop of operation. The control is provided predominantly by the system, and system-human interaction is the typical form of interaction. And then in the last stage, which is the executive controller region, the system closes the loop of all operations. Only system components are taking part in the control and the execution. The human may start or stop the operation whenever, for instance, danger is detected, and the system-system interaction is something what the system self-organization can also facilitate. So this is about the relationship, but obviously this sort of relationship shouldn't be taken out from the context. And let's talk about the context a little bit. And let's talk about the fact that when you define interaction, not only explicit context, the context in the nearby surroundings, but other more abstract element of the implicit concept should be taken into consideration. I would like to focus on this because these are closely related to those activities what you have seen on the for me the right outermost uh, column earlier, when the human is thinking, when the human is making decisions, and the human is initiating action. So implicit context refers to the tangible information related to the objective and the purpose of working with a cyber-physical system. Actually, the implicit context information is originated from the type of the, or let me say, the synergy, the expected synergy of cooperation, which should be established between the system and the human, or the human and system. And it can be cooperation, which is based on information sharing and mutual support. It can be coordination with shared and compatible goals for the human and the system, and agreement on the common task. It can be also collaboration, which means a collective purpose for the human and the system, and also means or involves an integrated strategy. And this is actually what manifests in cooperation. And then the next level is the coordination, which actually there is a very strict interaction structure, and the structure, however, not just covering the logical way of working, but also, for instance, the mentalities, a combined culture. Just consider what I said, that if cyber-physical systems are culturally adopted and embedded in the matrix of the society, these issues are coming up. So here we can identify a kind of integration level, which tells about how to consider the implicit context, and obviously it goes goes from a low integration level to a high integration level with regards to the implicit context. So what is new element here, that the implicit context remotely frames the reasoning and the organization of the implementation of dynamic interaction between the partners. So now let's come back to the explicit context of interaction. Explicit context, as we were talking about it, refers to the context information in embedded in the narrower or broader surroundings of the cyber-physical system. So what it means for us, that all interaction should be placed and imagined in a certain space and even location, and at certain points and within a time interval, with the involvement of certain actors, with certain goals to be achieved, and following certain rules or conventions. So the total of the structure information related to these constituents, the five that I just mentioned, these are the explicit context of interaction, and that should be also structured together with the implicit one. The total of the structured information about the objective, motivation, plans, history, trend, and so on also contribute to the implicit context. So the next topic is the various domains of interactions. And here, just a general model, what I can present, because actually it should be operationalized in concrete application context. But at least here you will see the reason why we, for instance, applied 4 domains for interaction at implementing our prototype cyber-physical system for stroke rehabilitation. So the domains of interaction between the system user and a ordinary technical system in principle can be the perceptive domain, seeing something, recognizing something, generating percepts. It can be in the cognitive domain, thinking, understanding, reasoning, forming opinion, decision making. In the motor domain, acting, capturing something, manipulating something, dismissing something, and also in the emotional domain, feeling empathy, feeling rejection, having hesitation, or working with care. And then what is interesting when we consider the domains of interaction for planning the interaction with the smart cyber physical system, we can see that in the interaction, the different domains may have varying roles. And this can be explained very simple with examples. Just consider, first of all, watching a photo viewer as an example, as a kind of activity for human and system interaction. You can actually diagram the situation with regards to the role of the domain, because obviously it is watching. So most probably the perceptive domain dominates, but we don't know how the cognitive, the motor, and emotional domains are proportioned here. So definitely what we can say that whenever we design interaction in the perceptive domain, we have to make sure that we set the level of the perceptive interaction to that level, and to achieve this with alternative means. Then the domains of or a second example for the domains of interaction and balancing or unbalancing that attention is playing a computer game, which is definitely in the cognitive domain. So obviously you have to see what you are doing, but this cognitive game can be all kind of, for instance, verbal, based on verbal communication or whatever. You need to have an engagement, obviously, because otherwise you don't do this, and you most probably need some motor action for the content. So here, when the cognitive domain is dominant, the same problem is here. Where to put the level? What we need there? And then, for instance, when we are talking about the motor domain of interaction, and then a representative example can be the steering and speeding a car, which is both are motor actions, because the steering wheel and the gas pedal should be activated. So definitely the motor action is important. Here it is obviously a discrete action which has nevertheless time aspect, but the logic of exerting the motor action and the timing of the motor action. This is why what needs more attention here. And then the last example is, for instance, being attached to a brand of the smartphone. It means an emotional experience with that. And then when the question of interaction design, that how to provide this attachment, how to reach this attachment, how to convince the user emotionally to use, for instance, a kind of recovery program or whatever. These are the issues here. But this decomposition is fine because it helps us to interpret different things, but actually we have to consider this as a totality when the perceptive, cognitive, motor, and emotional aspects are to be addressed in sufficient articulation and in applying a kind of balanced comprehension. And this is the problem, how to design it, how to make the best interface, which is a kind of balancing between the four aspects. And this is what is called in the literature, for instance, holistic interaction. And for instance, that sort of rehabilitation system, what I presented earlier, this definitely based on this. So the last topic, what I would like to include here is the modalities of the interaction and the main mechanism for transformation of physical energy into nerve impulses, sensory transaction are, for instance, the vision, sensing, gaze, light, audition, hearing, speech, voice, haptic, tactile, proprioception, then thermoception, obviously, olfactory, smell, gustation, taste, somatic balance, nociception, motion, gesture, and they are or can be strongly interrelated. So at the challenge at the designing interface for cyber physical system, more sophisticated interface than like a computer interface, is the consideration of the best modality for the interaction and the combination of these. This is what this particular figure tries to imply. And the last story is also interesting. It is about the level of interaction with cyber physical system. Because if we consider them as agents, the human stakeholder and the cyber physical system, then, and we assume that there is a physical connectivity between them, then we can say that the lowest level of interaction can be on the statistic level, when certain signals are transmitted and certain signals are received. Then we have syntactic level communications, and certain representation, if you like, languages are used, and based on the languages, this representation is understood. Then on the semantic level, we communicate thoughts, and the meaning of the thoughts is something what should be comprehended. We can go even further. So not only the understanding, the comprehension can be the goal, but also the success of execution. And this is what belongs to the pragmatic. Because pragmatic means that we have a expectation towards the action and its execution, and then we have a observation on the executed action. So how much they are the same, the expected and the realized. This is the issue on the development of pragmatic level interaction. And then the highest level is the aphobatics level interaction, and this is very important to be considered for the reason because actually we are going from the services, and not just the service provisioning and completion of the service provision is important, but also the reflections of the service receiver, what sort of emotional values, what sort of experiences it creates. So the apologetics level is about the intent, the target, what sort of emotional effect you want to achieve, and then you can compare it with, or you can see the results in the achieved result. What is important here is to see that gradually from the traditional transfer through the interpretation, through the meaning elaboration, and then the operation analysis, we go to the level when the success is expressed in terms of emotion. So this is a new model for organizing the level of interaction, and especially these two, the upper two levels, these are what needs to be further attention. In our past research, we did a lot of research and have a partial understanding, but still a lot to do here. And then, obviously, I have to tell you that by putting cyber-physical systems into social context, we also have to consider their interaction with the embedded environment, the cooperation with other systems, dealing with other human populations and enabling human individuals. And also, for instance, if they are personalized for their behavior, then they may behave as crowd actors, or behave as affiliated actors, or maybe behaving as autonomous action. So it means that again, the adaptation, which is on this level, goes to the socialization and goes to the personalization. This is the mainstream, the current mainstream of talking about interaction. So some proposition, the change role of actors of cyber-physical system raise the need for reconsideration of the current interaction theories. New design principles are needed, especially when the system makes the initiative, and also we have to consider the system-system interaction levels, domain, context, modalities of interaction should be considered in a holistic manner. I mentioned it in the presentation. And then designing proper interaction on pragmatic apoplectic level requires personalization and adaptation. And then both explicit and implicit context need to be evaluated early in the design for interaction with cyber-physical system. And the interaction with adaptive and evolving cyber-physical system needs more research attention. Very briefly, the suggested literature. This is the paper which summarized our work in 2015, and it gives a detailed introduction of the topic of multi-aspect interaction. Then emotional analysis in non-machine interaction is the title of the second paper, what I recommend you. And then aesthetic interaction, a pragmatic aesthetic of interactive systems. It is something about the apologetics and how to consider that level in the interaction. And then machines in the triangle, pragmatic interactive approach to information. This is about the pragmatism of interaction. And the last paper is a survey of robotics and emotion. It's important to see that how the soft aspects of interactions are considered in the robotic system. So this was the end. This is the end of the first block, and it was a little bit longer, unfortunately, than I planned. But I thought that the discussion is needed, so I stopped sharing. I don't know, is there any burning question at this very moment?
Any question?
Excuse me, sir.
Greg, you have some question?
Yes.
Yes, sir. Sir, I wanted to know what is exactly the pragmatic experiments. We talk about pragmatic experiments.
Yeah. Pragmatic. Pragmatism is actually reducing the solution of the problem to a manageable level. So the pragmatism means to do those sort of things which are really needed, those things which are really effective, and not, let's say, overshooting the problem. So on the pragmatic level, actually, what is dominating the achievement of the goals with the simplest approach. So when you design the interaction on the pragmatic level, you have to ask the question from yourself: how can I guarantee that the solution of the problem achieved with the simplest interaction? This is the pragmatism. And as I tried to explain, the apobatics about them, it also considers, in addition to this sort of simplicity or effectiveness of solving the problem, that if you do the problem solution that way, what sort of emotions, what sort of reflection, what sort of experience it raises in the people. And obviously, it goes far, but the experiences of the systems may be also taken into consideration in the future. So this is the pragmatism, and this is the apobatics. Thank you.
Okay, got it. Thank you.
I believe the time is pushing us, and the next topic, which is related to a overview of digital twins, might be also interesting for you. And if Professor Tandon agrees with me, I try to shorten this block presentation after showing a video which explains the essence. I just briefly revisit the basic concept, and then we will go into a conclusion. So now I share the screen again. Please give me a note if you can see the screen. I hope you can.
It is coming. It's visible.
So very briefly, and I apologize for this, but there are so many things to talk about that even with this many years of experience, I cannot properly handle it. Sorry for that. But let's go into the digital twins concept, and let's see what they are. Because if you take a paper on digital twin, it doesn't talk about anything. You don't know the context, how to interpret it, and especially not what you really need in the context of cyber physical system. So let's try to understand the realm of digital models first, because there is a difference between the digital model, or often called the mirror, the digital shadow, the digital twin, and the digital thread. I don't know if these terms are, or phrases are known to you, but I would like briefly explain it to you. So the most trivial thing is the digital model, a computer-aided model, a computer-aided engineering model for simulation. These are the digital models. According to the latest terms, they are called mirrors because they reflect either an object or reflect a phenomenon which is to be analyzed, especially in engineering context. So the digital model represents the relevant characteristic of the physical entity in bits, for instance, the digital CAD models, what I mentioned. The digital shadow is actually having a digital representation, but the main goal is not that, but keeping the physical entity aligned with the current status of the digital model. Now, an example. Just consider what is 3D printing. The 3D printing machine receives the control information time to time And then you have to download the control information in a space as the material can be deposited and as it solidifies. So in this case, actually, the digital model is conveying one-way information because typically no return of the information in case. So it is a kind of downloading the information. And then we have the digital twin, which is going beyond that and creates a two-way communication bridge between the physical world and the cyber world. It's also apply the cyber physical compute principle, but doesn't represent and doesn't substitute a cyber physical system because the goal is different. And then the fourth term, what we have to be very clear about is the digital thread. And the digital thread concept has been introduced to keep track of the evolution of the physical entities. And very recently, I came across a paper which is talking about the digital thread of cyber physical systems as such throughout the life cycle. So this is the notional presentation of these sort of things, but we also may approach it from the point of view of level of integration between the domains and the bridge building, the strengths of the bridge building. And then we can say that the digital mirror, or more commonly the digital model, no self-driven data interaction between the physical entity and the digital entity. So actually, the digital mirror model is created in a virtual space without any relationship apart from the mental cognitive idea about the physical object in reality. Then the digital shadow with regards to the integration provides a self-driven unidirectional data flow between the physical entity and the digital entity. This is what I mentioned, the digital model or process model of rapid manufacturing and the physical entity information. Then the digital twin is a direct data interaction between physical entities and the digital entities, and this is fully integrated bi-directionally. The digital thread from a information integration point of view is a communication framework that allows a connected data flow and integrated view on the assets data trends throughout its entire life cycle. So this is my first thoughts, and then let me show you a video which I believe sorry, I am tired. I shouldn't stop with it, but go into here, and then using all the bandwidths, you can monitor this particular. Just a moment. I hope it goes through. Yes. So this was the video, and then let's come back to my presentation and let's elaborate on a couple of slides and just let's offer the other ones for you for follow-up study. So as you heard, or as you could read, actually, the digital twin is a sophisticated virtual replica of one or multiple interrelated and complex real-world objects. The replicated physical objects and operating environments are continuously updating their digital counterpart with data or information. This way, the digital twin bridges the virtual cyberspace with the physical manifestation space runtime in a direct and quasi-zero-time manner. Digital twin is maintained and used throughout the whole life cycle of the object it replicates, from cradle to grave, we used to say. Digital twins can be used to plan, optimize, and simulate operations without the need for physical entities, serving as a comprehensive sources of information about their counterpart. There are notional elements related to every digital twin, and this is the first one is the computable rendering. It includes including complex of interrelated mechanisms and data constructs to represent connections between the physical reality and the corresponding interoperating virtual surrogate. The physical realities is the second notional element, include natural objects, artifacts, processes, people, places, systems, other formations. The virtual representatives are the highest fidelity, data-integrated, interoperable digital models, procedures, and mechanisms, and the digital connections are established by generating real-time data using sensors and processing them in a pre-programmed and runtime generated model. So digital twin actually should be seen as a data construct, and the data construct can start out or building the data construct can start out from CAD model data, for instance, and it can be expanded with procedural data, process data, getting to the computer-aided engineering models, and then behavior and state data can be affected, as well as environmental data. So this is the enrichment of the data construct of digital twin. And then it can be extended further with the beginning of the live data, the middle of live data, the end of the live data, and in general, the life cycle data. And then, obviously, it can be extended with objective description, performance specification, and any type of auxiliary data. So during the life cycle, multiple digital twins are created related to different domains and life cycle phases. The cognitive digital twin concept has emerged, and it is proposed to empower digital twins with augmented semantic capabilities. A conceptual architecture was proposed according to the ISO 42010 model. So the bidirectional linking is the most important element because if you have, for instance, the digital twin of products and services, and you have digital twin of the production environment, they can collaborate and provide a different type of intellect for each other. For instance, the production environment, the digital twin of the production environment can provide monitoring information, adaptation information, updating information for the digital twin of products and services, whereas the digital twin mentioned second time can provide alarming if there is any deviation, for instance, in the production environment. It may start negotiations for a better solution, and it may keep reporting. What is important is that actually somehow the human should have the opportunities to monitor all these things, and this is referred to as the big brother position, which is actually for the human assisted with systems which are making capable to monitor what is happening actually on the digital twins level, which is a very high complexity. So the placement of the digital twins means that system manifestation, models, relations, stakeholders, system conditions, states, data, characteristics, system behavior, analysis, simulation, behavior are the main aspects to capture. And then based on this, various digital twin services can be provided, for instance, system monitoring, system maintenance, system optimization, system sustenance, and system evolution. Here I would like to stop with the slides and just to show you the next slides because they are many, in fact. Sorry for that, but there is one image what I also would like to show you, namely the process of digital twin integration. And it starts with analyze the system model and architecture and build a reference digital twin models for instance, the cyber physical system. Instantiate a digital twin model with initial configuration data, optimize the digital model with operational data, and then adopt the system towards the optimal operation, and then apply continuous monitoring and planning and reconfiguration. So this is the and obviously shut down and switch over to fallback procedure or redundancy whenever it is needed. So this is how the digital twin organization process can be used. There is one more image what I believe meaningful for you to share or to know about, and this is the differences on views, differences of the views between the academia and the industry concerning the cyber physical system. The academic view is that the digital avatars are developed, the digital twins are developed to be digital avatars and integrated simulation of complex systems or dynamic virtual representation of physical system across its life cycle. This is the major target. The industrial view sees digital twins as the engine behind the digital factory. And in this case, a high fidelity representation of the operational dynamics of the production assets based on near real-time synchronization is considered. So we have a gap here, but I believe what is important in the future and for the researchers to try to approximate and mirror these two views. And obviously it means that we need a kind of holistic view which considers digital twins as computable meta or even mega models of tightly integrated physical and virtual models covering the whole life cycle of complex systems. Here, the complexity again, what is to be considered. So at the end of this second block in this presentation, let me suggest a couple of literature. Digital twin, manufacturing excellence through virtual factory replication is the first one. What I suggested, this is the initial paper from Greece, actually based on which the concept of the digital twin was introduced in academic circles and everything else in the industry. For instance, the Philips, not only NASA, but also Philips and Siemens have made a lot of studies related to that. So one of the gurus, Taro, wrote a paper in the Nature, surprisingly in the Nature, not long ago, make more digital twins. This is what he is urging for. And then Betty's paper, The Digital Twins, it's a very comprehensive and useful introduction into the topic. Then Digital Twins-based smart manufacturing system design in Industry 4.0 review is the next one, what I would say, for instance, where Sean is involved here. And then Greaves and Vickers presented a paper in 2017, Digital Twin, Mitigating Unpredictable, Undesirable Emergent Behavior in Complex Systems. Unfortunately, I didn't have time to talk about the emergent behavior and capturing the emergent behavior in digital twins, but you may refer to the existing literature, and this is one of them. And then again, Tao and the co-authors paper on digital twin in industry, the state of the art. So this concludes my last presentation today. Sad, isn't it? But this lecture was the last in the package. The first block tried to sketch up the major concepts of digital twins, and the second block focused on the trend in the development of application of digital twins. Thank you for great interest and contribution. Thank you so much. And this is the end of my presentation. I stop sharing. If you have any questions, don't hesitate to pose a question.
Imre, I'll request you to share the last slide of your presentation.
Last chance in this course. Last chance.
I'd like to take a photograph of that, a screenshot of that. Handshaking. Thank you very much for a very wonderful series of lectures. They're very informative, and I'm sure that all the participants must have gained tremendously. Now it's up to the participant to start practicing and make it as a part of the practice. Right?
I believe you understood, and now you can see clearly the uniqueness of this presentation. So it is dedicated to cyber physical system integrators, not for specialists. And with this knowledge, if you deepen in this, you will be in an easy position to take industrial jobs and to convert this knowledge into the benefit. But as I said during the first lecture, obviously this is just our assistance to your automatic learning or autonomous, better to say autonomous learning, and please select that particular field what you are more interested, and this way you can form a kind of T-shaped expertise for yourself. Thank you so much again.
Thank you. So any question anybody has? No question? Please, all of you are requested to kindly switch on your cameras. Vijay, are you there? Okay. By the timing, we can take a photograph. Okay.
Pune, as a last word, obviously I'm very grateful for every participant for following me and giving me the opportunity. But I really would like to thank and make a comment on the contribution of Mr. Vasanta. You helped me really a lot with your questions, and actually every moment when you ask something, even when I struggled with hearing problems, I mean because of the voice transfer, I always felt that, and I saw on your eyes that you are understanding it and a kind of interiorizing this, and I clearly saw it in your eyes. I must tell you. So, like to the other colleagues who participated, I want to wish you all the best and please profit from this knowledge what how to say was presented, delivered to you this time. Thank you, Pune. These were my last words.
Thank you very much, and thank you for sparing so much time in not only delivering these wonderful lectures, but time spent in preparation of these lectures, which is significantly more. So hope we'll be able to rope you for another collaboration, maybe some teaching assignment, maybe some research common, which is more closer to our heart.
We go on.
And
That's
definitely we'll meet physically sometime very soon.
yeah.
In
I
India
hope
or somewhere. The next time if GIAN offers the course in a physical mode, we'd like to have your present in India. But that will definitely enhance the quality of lectures being delivered by you. Thank you very much.
I'm also pushed my wife, so most probably this helps to realize things very soon. What I would like to mention as the last, really the very last word, I wish a successful examination for the students and good results, which shows or reflects our effort. Thank you so much for the time, and bye bye for everyone.
Bye. So I'll just maybe within a minute or so, I'll be mailing to all the participants the end of the course quiz. You have 1 hour to write the exam, and 1 hour is more than sufficient. So think coolly, answer all the questions. It is a PDF file. If you can write on the PDF file, you can do it. Or maybe you can write answers 1, 2, 3, 4 in separate doc file, convert to PDF file, and mail it back. Please make sure that you write your names and your GIAN registration number, your email IDs and your phone numbers on the top page of your sheet, and mail all those files before 5:30 to the same email ID from where I am sending these mail, that is cps.gian@iitmj.ac.in. Any question anybody has? I'll keep this session live, although I'll stop recording and I'll stop live streaming. So if anybody has any question in between, or we can meet once again at 5:30. And so to have a virtual valedictory, virtual bye-bye. So any question anybody has, or